Hello, welcome everyone to our TUM AI lecture. Today it's a pleasure to have Chelsea Finn with us. She's a professor in computer science at Stanford, where she's leading the IRIS lab. Her research studies the intelligence through robotic interaction at scale. In addition to her professorship at Stanford, she also spends time at Google, where she's part of the Google Brain team. Well, and I think mostly everybody in the robotics community and probably in computer vision now too knows Chelsea's work. She's very famous for the meta-learning papers, and there has been already a lot of follow-ups in actually all kind of communities now. So this is a true sign of pioneering impact very early in a career. So I think this is what a lot of young researchers are aspiring to do right now. So it's a real pleasure to have you here today. And really curious to hear what you're going to talk about.
Absolutely. Thank you for having me. And yeah, excited to share some of our, I guess, what we've been up to in the past year or so. So to start with a bit of motivation, I'm going to start actually with a story from my PhD, which in particular, we wanted to figure out how we could get robots to learn. And we wanted to figure out if robots could learn neural networks that map directly from cameras from the robots, images from the robot's cameras directly to torques applied to the robot's joints. And so in this video, you see kind of the end result of one of those efforts where the robot is learning from scratch how to place this red block into the corresponding slot in the shape-showing cube. And over time, through deep reinforcement learning, the robot is able to figure out how to solve the task. And I found this pretty cool that we're able to do this, and we're able to learn neural networks end-to-end from scratch for both visual perception and control simultaneously. And so here's the final policy. You can see that I'm kind of holding out the cube for the robot. You can see the robot's point of view in the bottom right. And this was pretty exciting, not just because the robot could play with this particular toy, but the robot could also play with other toys, like putting the claw of a toy hammer underneath a nail, figuring out how to screw a cap onto a bottle, and in some follow-up work, being able to do a more complex task, like using a spatula to lift an object into a bowl. So this is all pretty cool, and this seems like a pretty natural way to train robots to acquire different skills autonomously. And around the same time, a number of people built on these ideas and applied reinforcement learning to their robots to learn other skills like hitting a puck into a goal, opening a door, and throwing an object to hit a target. And around the same time, we also saw some successes with deep reinforcement learning with Atari, AlphaGo, Locomotion, and so on and so forth. This is, I mean, arguably a pretty exciting time for reinforcement learning and for robotics as well. However, we also have a problem with these approaches. They're really exciting, and they're kind of clearly seem like a pretty good way to go about learning different skills. But the problem is that in each of these videos, what you see the robot doing, it looks maybe somewhat impressive, but the robot isn't learning kind of general purpose skills that can be reused across many environments, across many objects, and so forth. Essentially, what the robot has learned is, for example, how to pick up that, how to use that spatula to lift that object into that bowl in that environment. And if you changed anything about the environment, like the spatula or the bowl or the object or the background, the policy would fail because that environment was basically, that all the data that it had seen is from that environment. And so it's learning one task in one environment starting from scratch. And if we ultimately want robots to be able to use many different spatulas and operate in the real world with many different objects, we need to, like, I don't know, rethink our approach, I think. This approach is kind of sort of analogous to kind of giving a baby on day one a spatula and saying, okay, learn how to use a spatula before you've learned anything else about the world, and only learn that one thing. So what I'd like to talk about today is how we might be able to get robots to generalize and ultimately move towards robots that can generalize to new objects, to new environments, to new tasks, and so forth, and hopefully take a step towards actually pushing robots outside of the lab and into the real world. And of course, this might have implications in robotics. It also probably has implications for intelligence more broadly as well, as these are things that are pretty basic. These are things that humans can do pretty early on. So what's the problem? I mean, one way to look at the problem from a machine learning standpoint is that our training distribution right now is in a lab, and it's in one particular lab with like one set of objects. And ultimately, we care about having robots be able to generalize to the real world. And so our desired test distribution is much, much broader than our training distribution. And so how do we go about solving this problem? Well, what I'd like to argue is that I think we need to basically broaden our training distribution. If we want robots to generalize broadly, we should train them with equally broad data. And why should we do this? Well, we've seen success stories again and again in the rest of machine learning, where if we train them on broad data, if we train object detection systems or things like GPT-2, Google Translate, GPT-3, these things actually work really well, and they work well in settings that are much more like the real world than any of the settings that I showed you before. And further, we also know that people don't just learn from an hour of experience. People accumulate and learn from broad experiences. And so it seems like in order to make progress in robotics, we should develop algorithms that can learn from scalable data sources and use very broad data sets. So then the question is, how do we actually go about doing this? One question is, well, there's a lot of computer vision data sets out there. Maybe we can use those computer vision data sets and use that to help robots be able to generalize to at least their perception system to the real world. And we actually have tried this a bit and haven't had as much success as you might hope. So one thing that we've tried is we've used off-the-shelf object detection systems, like, I mean, these might be a little bit out of date at this point, but things like Mascar CNN, YOLO V3 or something like that. And in particular, we had this mobile manipulator right here. And we took images from the robot's camera. The robot's camera is actually right here. And so it's pretty low to the ground. And you get images that look like this. And I think these images are pretty different from what you typically see in computer vision data sets. And so there's a lot of domain shift. And in order to get these systems to work well on these images, you need to actually collect label data from this camera. And this is actually pretty annoying because then that means that maybe for every new environment, you might need to collect additional label data from that environment, from that robot, and so forth. The other issue that we've found is that there's actually a lot of objects that are kind of outside of the set that these object detection systems are trained on. And so it was pretty difficult to get these to work and be useful for this kind of problem. Now, of course, maybe we shouldn't take systems off the shelf. Maybe we should fine tune them. And so we've also tried running reinforcement learning, fine tuning from ImageNet features. We've tried this in a number of different projects and mostly have anecdotal evidence, although there's one paper where we had more quantitative evidence where we wanted the robot to be able to generalize to new test environments. This table has a lot of numbers, but kind of the key thing is right here. Whereas if you compare learning from scratch to learning from ImageNet features, you really don't see any big benefit from using ImageNet features. And I think there's a couple of reasons for this. I think that one could be some of the reasons like what we saw before with domain shift and objects out of set. And then I think the other reason is that to learn these kinds of things, you don't just need a good perception system, you also need good action representations. And if you initialize the perception system very well, but don't initialize your action representations very well, then you don't get very good performance. Okay, so what I'd like to talk about today is those are some maybe anecdotal failure cases or negative results that haven't been as successful. So what can we do to try to be a bit more successful? So first, I'm going to talk about how robots can acquire broad and diverse experiences. How can we get data sets that are useful for robots that are also very broad? And second, how can we have algorithms learn from those scalable data sources? And I'm actually going to cover two parts of the second one. First, we're going to be looking at how we can use very broad robot data. And then we're going to be looking at how we can use actually data from humans, so videos of humans doing tasks. Okay, so let's first talk about how we should go about collecting data and collecting broad data sets for robots. One approach is robots can actually fortunately collect their own data, which is pretty nice. And so we could just run a very lightly scripted policy that takes random actions on the robot, and you get videos that look like this. And you can actually collect a lot of data this way, because you could actually run this data collection overnight, 24/7 almost. And you also get actually surprisingly rich interactions here. You get some pretty interesting data, lots of, a fair number of interactions with objects and so forth. And so this has kind of been our very kind of attempt number 0 at collecting very diverse data. And in addition to just collecting data on our own robot, we've also taken this approach and tried to actually scale up data collection across different labs. This also means that we're collecting data across different robots as well. And by doing so, we might be able to kind of move towards the rest of machine learning, where we're sharing data across labs, across robots, across environments. And so we collected this data set that we're calling, shamelessly, the Robonet Data Set. It has 7 robot platforms, 15 million video frames, 113 camera viewpoints. It was collected across 4 institutions. So this is essentially kind of maybe a sort of V0 towards really broad and diverse robotics data sets. And we're hoping that something like this can be useful for our algorithms that I'll talk about in the second part of my talk. Now, of course, this is still random data. And so we can collect a lot of data this way, including data of like deformable objects, for example. But the utility of this data is limited because we won't be able to learn very sophisticated tasks this way. The robot won't see interactions they won't see data that's kind of similar to more complex tasks that we might want the robot to be able to solve. So can we collect some more interesting data that's more like the kinds of tasks that we want robots to solve? So one approach might be to provide some demonstrations. So you can guide the robot arm through certain motions, similar to the kinds of tasks that you might want it to do, like using a tool to solve a task. And this will give you pretty interesting and useful data, because you can basically guide the robot to do lots of different sophisticated things. However, you can't collect that much data this way because this is a pretty time-consuming process and it requires a human in the loop of the data collection. Another source of data that I think is actually quite promising is, instead of using kind of robots, like teleoperated or kinesthetic teaching on robots, is to use videos of humans doing tasks. And I think this is really promising because humans are already doing lots of different tasks in the real world. And there's also just data that already exists of humans doing tasks. And these are really interesting and sophisticated interactions, and a lot of the things that we'd love for robots to be able to do as well, like cleaning dishes. So this leads to lots of really interesting data. It is much harder for a robot to use this data because it's not the robot doing the task, of course. But it's something that I'll come back to later, and I'll talk a little bit about how this data might be useful for robots. So this still leaves the question of how we can scalably collect useful robot data. That's pretty interesting. And so to try to answer this question, we next looked at a class of methods that try to explore the environment in a completely unsupervised way. So before, we were just executing random actions on the robot, but there's all this literature on curiosity and seeking out novelty. And so maybe we could apply these methods to the robot. And in particular, what we wanted the robot to be able to do is open these drawers. And so we ran a novelty seeking method on the robot to try to see if it could explore its environment and also collect data of opening these drawers. And so we took the plan to explore algorithm, which is one of the state-of-the-art algorithms from ICML last year. And unfortunately, when we ran it on the robot, we saw that it sometimes interacted with this drawer, but ultimately, I think that the environment was much more complex, much more rich than a lot of the simulated environments that these kinds of algorithms are tested on. And we never saw that it actually opened this drawer at all, basically. And it really didn't actually interact that much with its environment. And so from there, we thought, well, okay, maybe a user can help the robot a little bit. And instead of having the user in the loop of the data collection process, like when we're collecting demonstrations, maybe the user can provide some guidance before data collection that helps the robot target its exploration. So we're going to try to have a user help the robot without having a human in the loop of data collection. And so the key idea of how we'll do this is we'll first show the robot examples of states that are interesting. So in this particular example, we can show the robot examples where the gripper is near the drawer, or the drawer is open, and so forth. And this is going to take just a few minutes to collect this data, because we're just going to essentially provide kind of tens of images, not that much data here. And then once we have these examples of interesting states, we can have the robot try to explore in that particular region of the state space. So first, we'll train a classifier that classifies between interesting examples versus data that the robot has explored. And so this is basically just a binary classifier that classifies between the human provided states and the observations that the robot has seen so far. And then we'll train the robot to explore to find images that are classified as interesting. And that's it. That's kind of the gist of the approach. And we'll use this in this example for trying to get the robot to explore the drawer. But you could provide other examples of interesting states and have the robot explore different parts of the state space. And you're essentially just telling the robot that this part of the state space is interesting and this is something that you should try to explore. Okay, so how well does this do? After about 3 minutes of providing these images and then running autonomous exploration, we found that the robot could much more effectively explore this part of the state space. And in this video, you see that the robot is kind of playing with the drawer, opening it, interacting inside of it, and so forth. And if we compare this approach that uses a little bit of human guidance to the fully unsupervised approach, which is using model disagreement, we see like a pretty massive difference in the amount of interaction with this drawer, either touching the handle or moving the drawer. So for me, the takeaway here is that a really small amount of human guidance outside the loop of data collection can really go a long way towards guiding the exploration process and guiding the data collection process towards interesting states. Okay, and then another kind of separate question is, can we actually use this data set to perform control? And so in a follow-up paper, we labeled 200 images as the drawer being open or closed, trained a classifier, which will provide the reward signal for reinforcement learning. And then we ran offline reinforcement learning on only that data set using this reward signal. And with that, you can learn a policy that can close the drawer. And this policy has about a 76% success rate. Okay, so in terms of collecting broad and diverse experiences and data sets, one takeaway is that really a small amount of guidance can help robots explore in interesting ways. And really a next step here, a step that we're currently exploring, is to try to scale up this form of data collection, not towards, not only for opening a drawer, but for lots of different environments and so on and so forth. And because this approach is scalable, because we don't need a human in the loop, it's something that should be easy to move towards collecting in diverse environments and so forth. Okay, so that's on the data collection side. Now, if we have very broad data sets of from robots or from humans, how can we go about getting algorithms to learn effectively from them and learn policies that generalize well? Learn policies that can generalize to new objects, to new environments, and so forth. That's what I'll talk about in the kind of next part of this talk. And we'll start by talking about how algorithms can learn from diverse and broad robot data. And in particular, because we haven't yet scaled up the interesting data collection that I just talked about before, we're going to be using this more random data that we've already collected. that has many different objects, including deformable objects and tools and so forth. Okay, so how do we go about learning from this data? In contrast to the problem of using a spatula to lift an object into a bowl, there's no like inherent task with this data. There's no notion of progress. There's no notion of success. And so it's not like we can't just train a policy to do one particular thing, also because we want robots to be able to do a lot of different things, not just one thing. And so what we're going to do is once we have this really diverse data, we're going to learn a predictive model. We're going to learn to predict future image frames, future video, conditioned on the current frame and the future sequence of actions. And this gives us video predictions that look like this, where if you feed in different actions into the model, it will predict different futures. And in contrast to what I was showing at the very beginning, these models can capture much more general purpose knowledge about the world, about physics, about objects, if they're trained well. And they also are fully self-supervised and use all of this available supervision signal, which means that it's very easy to apply these algorithms to broad data sets and even data sets that aren't labeled. And lastly, there's also no assumptions about the task representation. You don't need to have a representation of objects for this to work. And so as a result, this means that you can apply these kinds of models to deformable objects, and you don't need to have a model or a good representation of what a deformable object should be, whether it be like a point cloud or a reconstruction or something like that. You can just kind of apply these video prediction models and you'll still learn a lot of interesting things about the world. And then the last thing that's good about these models is that prediction is a fully supervised problem. And so in principle, if you can scale up these models effectively, we should be able to get very good predictions. And so all these predictions are actually from fairly old models. And if you take a model from NeurIPS in 2019 that's quite recent, where they basically just scaled up these models and applied them to the deformable object data set that I talked about before, you actually get predictions that, at least in my mind, look pretty impressive for actually predicting the motion of these deformable objects. Okay, so these models seem pretty cool and pretty nice in the sense that they're learning a lot about the world, about interaction and so forth. How do we actually use them for solving tasks? So what we're going to do is we're going to take these models and actually try to plan using them in order to solve tasks. And this will essentially just look a lot like model-based reinforcement learning or model predictive control, if you're familiar with that. And so what we'll do is we'll take our current image frame. We will consider a number of different potential action sequences that we might want to take, maybe these two action sequences. Then we'll predict the future for all of the action sequences that we're considering. And then for the prediction that is the closest to what we wanted to accomplish, we'll execute the corresponding actions. And then we can reiterate these first three steps at each new camera frame that you get to continuously replan the actions that you take. We in principle use a slightly better optimization process to get action sequences in this, but this will get across the key idea. Okay, so essentially the way that this works is we take our data set of robot data, we learn this predictive model, and then we plan using the model to accomplish tasks. We call this visual model predictive control or visual MPC, and the paper also calls it visual foresight. So we made the mistake of giving two names to it. Okay, so how well does this actually work? One of the things that's pretty cool about this is you can actually use a single model to solve not just one task, but many different tasks. And so if you train this model on random data and plan, you can get the robot to pick up an object when you specify a particular goal. You can tell it that you want to move a towel to cover an object, and it can figure out how to solve that using the video prediction model. And these are objects that were held out and not seen at all in the data set during training. So the robot is generalizing to new objects and also to new tasks because it didn't actually see any supervision in the data collection process. And then also if we give it slightly better data, if we use some demonstration data, we can solve more complex tasks like tool use. So here's an example of using a broom to sweep things into the dustpan. We can also tell the robot that we want to move the blue object closer to itself, and it can pick up the hook and accomplish that task. And then you can also figure out how to use unseen objects as tools. For example, I think it actually never seen any sponges before. And I figured out that in order to sweep the red objects off of the plate, it can pick up the sponge and use it to sweep them off. Okay, so this seems pretty cool. Now, what is the bottleneck for really scaling this up towards much more diverse data sets? Well, what we did is we took these video prediction models and we applied them to the Robonet data set that I mentioned before, which is data across labs, across environments, across robots. And so here are some example videos from the Robonet data set, including, I think this shows like 4 or 5 different robots. And if we took that really nice model from Ruben Villegas et al. From NeurIPS 2019, it predicted very nice things on the deformable objects from the Sawyer. However, when we move it to this more diverse data set, the predictions look considerably worse. So it isn't able to really even predict the kind of motion of the arm of the robot very well. Now, what's the problem here? So these video predictions, these aren't actually even, these are from the validation set, but these predictions are actually representative of the predictions that you see on the training set. And so the issue here isn't even that it's just failing to generalize. The issue is that it's underfitting and it isn't even able to fit the training set. And we also just took a model and trained it just on the Sawyer robot portion of Robonet, and we still even saw underfitting there. And so, for example, we took a 75 million parameter model. We also scaled it up to 500 million parameters on a TPU. And we see that there are blurry arm predictions. These do get better when you make the model considerably larger. We also see that there isn't really any object motion prediction, and the object motion prediction improves a little bit when you move towards the much larger model. But even with this kind of narrower data set that's only the Sawyer robot data set and a larger model, we still see actually a lot of underfitting with these models. And this seems actually, at least was to us, somewhat surprising, because underfitting isn't normally an issue that you see with deep neural networks. So from this, we wanted to figure out how we might be able to build dynamics models, build video prediction models that can better capture this kind of data. So the first thought that we had here is maybe instead of predicting full images, maybe we can predict representations that only capture what really matters to the robot. Of course, one approach that you could use here is to use some supervision about the task, learn a representation that's useful for that task, and then predict in that representation space. This is basically just like standard state estimation. And if you do something like this, this is kind of done in a lot of different papers that try to recognize objects, for example, or even systems like Planet that use the reward signal. And generally, these approaches work really, really well if you can get a lot of supervision and if you know what a good task representation is. But of course, it requires significant supervision and significant engineering per task. And so it doesn't seem like something that will really scale towards really kind of broad and diverse data sets and towards the kind of like open set tasks that we want robots to be able to perform. Separately, we've also explored how we might learn representations like this in a self-supervised way that are tailored to a particular goal image. And we refer to this as kind of goal-aware prediction, where you try to learn representations that are useful for reaching a goal image and then discard information about objects that aren't relevant for that goal image. And so this actually can work without any supervision. And we have some evidence that it can successfully redistribute the model errors to care more about the objects that are relevant to that goal. But it's kind of an initial approach towards this direction, and I think that we really need more research to figure out what how to learn representations that capture the things that we care about in self-supervised ways. So we only have kind of preliminary evidence that this might be promising. Okay, so from there, given that learning representations seems to be difficult, the next approach that we really tried to look at here was actually just trying to make the dynamics model bigger. And one practical bottleneck that we run into here is limited GPU memory. And of course, you can do things like model parallelism and so forth, but that ends up being pretty taxing. And you can only, it also kind of increases the number of GPUs that you require and so forth. And so one thing that we looked at is there's this old trend of training neural networks layer by layer. And for example, here are a couple papers that do this. And the way that they work is they train the first layer of the neural network by just training like a one-layer neural network. And then they train the second layer that kind of reconstructs this middle layer, and so on and so forth. And one thing that you can note is this greedy training, it reduces memory costs because you only need to train one layer at a time. And it also was actually used to address some kind of optimization challenges at the time of training neural networks, because this provides a little bit of a curriculum. And so we thought, well, maybe we could take this sort of greedy training idea and apply it to video prediction models and use it to actually get much larger video prediction models. And so what we did is we first train essentially like a one-layer video prediction model. We then freeze this first layer that was trained in the previous stage, and then train a second model, the second layer essentially of this neural network. And we repeat this process k different times to train these k modules, where at each step we only train the kth module and refreeze the previous modules. And this can save memory in basically a couple different ways. It's not going to be saving quite as much memory as we saw with the previous kind of layer-wise autoencoders, because we're still going to be training it to reconstruct images. We found this to be important rather than just reconstructing activations. However, we don't require kind of a full backward pass through this part of the network because this part is all frozen. And that does actually end up leading to pretty significant improvements in memory usage. And the second thing that we found is that we also found that this can actually make the optimization a little bit smoother as well. One of the kind of local optimum that you see in video prediction model training is that sometimes it just likes to predict the first image and just repeat that image throughout the video sequence. And with this sort of curriculum of training a one-layer neural network and so on and so forth, we found that it didn't really fall prey to that local optimum. So there are a bunch of details to the architecture, but the high-level bits is that we're training these modules sequentially. We're optimizing each of the modules with respect to the evidence lower bound of the next frame. And then one last bit that we found to be pretty important is we're using latent variable models to capture the stochasticity of the future. And when you use things like VAEs, you need to impose a prior on that latent space. And that prior makes the kind of this mean field approximation where it treats all of the dimensions as independent. And in images, if you just flatten a kind of spatial feature map, then you're actually going to have significant correlations between neighboring pixels. And that kind of violates this mean field approximation that different dimensions are independent. And so what you can do is you can try to have your encoder really compress the spatial dimensions and expand the number of channels. And this will prevent these sort of correlations in the latent variable. And we found this to be pretty helpful for performance. Okay, so how does this video prediction model compare to previous methods? We wanted to compare them to state-of-the-art video prediction models, of course, and in particular, the kind of largest scale video prediction model that we are familiar with was this prior paper from NeurIPS 2019. We also wanted to look at whether this led to better downstream planning rather than just leading to better video prediction quality. And then also we were interested in how this compares to end-to-end training, and if we can start to get these models to stop underfitting. And so in terms of metrics, we looked at FVD score, which measures visual quality and temporal coherence. It's a reference-free metric. We also looked at LPIPS, which measures perceptual similarity to the ground truth. And then we also looked at human preference. And what we found is if we compare these greedy hierarchical VAEs to this prior model from Ruben Villegas, which is a scaled up version of SVG, we saw a pretty significant improvement across the board. So we saw about a 20 to 50% improvement in FVD score and in LPIPS. And we also saw a pretty significant improvement in the human preference as well. Okay, now how does this actually translate into better downstream planning? We looked at 2 different classes of tasks. And in each of the tasks, the goal was the robot had to pick up a sponge or an object and use that to move a object either into a dustpan or to move an object off of a plate. And in this case, we gave the robot a goal image, and it had to try to plan in order to match that goal image. And so in this first case, we see the robot is able to use the video prediction model to sweep the object into the dustpan, and also in this case to sweep the object off of the plate. And one of the things I should mention here is when we ran these experiments, we actually pre-trained the model on Robonet and then fine-tuned on a small amount of data from this robot in this environment. And if we train this model, we didn't actually have that much new data from this robot in this environment. I think it was a few thousand trajectories. And if we trained a model from scratch, it didn't work very well at all. But the pre-training on this very large and diverse data set really improved performance here. And again, all of these experiments are with objects that the robot has never seen before. So this is testing generalization to new objects. And then if we look at the success rate, we see a pretty big improvement in the success rate of the robot for these 2 tasks compared to the previous model. This is exactly like what we like to see when we improve the underlying models. Okay, and then the last 2 questions is we wanted to understand this model a little bit better. And so we first compared this kind of greedy training scheme to end-to-end training. And we were expecting to see end-to-end training to be about as well, maybe actually a bit better than greedy training because it can train end-to-end. And in reality, we actually were surprised to see that greedy training actually performed a lot better than end-to-end training, at least for this particular model architecture. And this suggested to us that end-to-end training was actually having a lot of optimization challenges, and it was actually plateauing, its loss was plateauing very, very quickly into training. And so it seemed like greedy training was leading to an easier optimization, at least for this particular architecture. And then the last thing we looked at is whether these models are starting to overfit on the Robonet data set. And if we compare the train and test loss, or the train and test metrics here, we still appear to be underfitting on Robonet. We saw overfitting on smaller data sets like Kitty, for example. But for this data set, we're kind of still reaching this underfitting problem, and this suggests that we need more research to build better models on this. Okay, so that's how we can use robot data and really try to build models that can scale to the breadth of data sets like Robonet. Now, what about using human data? So I mentioned before that human data could potentially be pretty exciting because we have a lot of really diverse data sets that already exist on the internet and so forth. And humans are doing really interesting things that are much more interesting than the kinds of robot interactions that we get if we run random data collection. And so we wanted to answer the question of whether we can leverage videos of humans to improve robot generalization. And in particular, the goal that we're going to focus on for this work is to try to learn a metric of task success or reward. So we're not going to be trying to learn how to learn policies that generalize directly. We're specifically going to be focusing on learning this kind of success classifier or learning a reward function. And this is still really useful for robotics because the robot can use it to figure out if it succeeded or not. And oftentimes it's a precursor to running reinforcement learning. And if your reward function doesn't generalize, then you're certainly not going to get a policy that generalizes. So it's worth mentioning that there are actually a lot of works that look at using human videos for robotics. But one kind of common trend along a lot of these recent works is that they typically use pretty narrow human data with fairly close similarities to the robot data. And so as a result, this narrow data is going to be less useful for promoting the kind of generalization that we want to see across lots of different tasks and environments and viewpoints. So in particular, for this, we actually turned to the something something data set. And you can see some examples of the videos here. They're really diverse. The videos are also categorized by task. They're partitioned by task. And it has many different environments, many tasks, many different people, many camera viewpoints, and so on and so forth. And so it seems like this might be something that we could use to try to improve generalization. In addition to this data set, we're also going to assume that we have a little bit of robot data. And in particular, this is going to be pretty narrow robot data just in one environment, demonstrations of performing a few tasks. So this is the kind of robot data that we can fairly easily get our hands on. It's getting the really broad and diverse demonstrations that are really difficult. And then we'll use all of this really diverse human data, a little bit of narrow robot data, to try to learn what we'll call a video conditioned reward function. A reward function that allows us to, that kind of provided a video of a human or provided a video of a robot, tells us whether or not, conditioned on that kind of that task specification, whether or not the robot is doing the task. This is kind of our training setup. And then at test time, we want to be able to generalize to unseen environments and unseen tasks. And so what we're going to be considering is we're going to be given a human video, for example, of pushing a tissue box to a left. Then we want to use this to get a reward function conditioned on this video in order to allow a robot to solve the same task. And it might be solving that same task in a different environment or with a different camera viewpoint and so forth. Okay, so how do we actually go about doing this? The key idea is actually really simple. We essentially just take all the data in the something something data set and our narrow robot data, and we train a classifier that takes as input 2 videos and outputs whether those 2 videos are doing the same task or not. And so, for example, we might provide these 2 videos as input. Both of these videos are showing a robot or a human closing a drawer. And so the label here would be 1. These are doing the same task. We would maybe provide the classifier with these 2 videos. These are doing different tasks, moving something away or closing something. And so we would train the classifier to output 0 for this pair of videos. And then we'd also use pairs of human videos. And for example, if we gave it these 2 human videos, the label would be 1 because both of these are closing something. Okay, so that's really the key idea. And once we learn this classifier that can predict whether 2 videos are doing the same thing, then we can give a video to this classifier and then pass in the robot's current behavior, and that will tell us whether or not they're doing the same thing, and that we can use this label or this prediction as our reward function for solving tasks. And we'll use this as a reward function for running the same sort of visual planning approaches that I talked about before. And we'll refer to this as kind of domain agnostic video discriminators, or DVD. Okay, so we first tested out how well this works in simulation, and we really wanted to test generalization. And so we had an initial training environment. This is where all of our narrow robot data came from. And then we had 3 different test environments. The first test environment was the same, but had different colors of objects and backgrounds. The second had different colors of objects, but also had a different camera viewpoint. And the third environment had different colors of objects, a different camera viewpoint, as well as a different arrangement of objects, because this coffee machine and the drawer are in different locations. And the tasks that we looked at included closing a drawer, pushing a cup to the coffee machine, and turning a faucet to the right. And so the first question that we have is, can we generalize to these new environments using the human videos? So to answer this question, we first looked at performance if we only use the narrow robot data. So we only use the data from that first robot data from that first environment. This is what we typically do. This is what kind of the robotics community typically does in robot learning. And what we see here is in the training environment, our performance is somewhat reasonable. And then after that, the performance decreases as you move towards these new test environments. And then if you add in the human data and use human data to train this classifier, we see that the performance is significantly higher, especially in these test environments. So these four kind of pink or purple bars all corresponded to using different amounts of human data. And so essentially by adding these human videos to our data set, we get an improvement in environment generalization by about 20%, which is pretty significant. What does this actually look like? So we provide a human video, for example, of closing a drawer. We then run visual planning with respect to the reward function that we get from DVD. And in the training environment, it can solve the task. And also in these other environments, it can also solve the task. And we can also give it a video of pushing the faucet to the right, then run planning with respect to the reward. And we find that it can solve the task in the training environment as well as in the held out in the new environments as well. Okay, and then the last question we asked is whether this allows us to generalize to new tasks. And so in particular, if we hold out human videos and kind of the robot data of the tasks that we want to evaluate on at test time, can we then provide a video of this new task to the classifier and have the robot be able to successfully perform the task? This table is probably a bit difficult to parse, but the kind of key things to compare are this red line, which only uses robot data, and this green line, which uses robot data and human data. And we again see about a 20% improvement in this sort of task generalization by using the really diverse human videos. Okay, and then the last question we asked here is, does this actually work on a real robot? And so our training data included, our training robot data included demonstrations of closing a drawer and pushing something from left to right. And then test time, we looked at a new environment and new tasks. And so our training data included this robot data as well as all of the human videos. And at test time, we then gave the robot a video of a person doing the task, and the robot is able to plan and figure out how to do the task using the DVD reward function. And lastly, we gave it a new task of pushing something from right to left, and the robot is also able to figure out how to solve the task. Okay, so to wrap up, kind of the key thing that I talked about is if we care about getting robots to generalize broadly, we need to figure out how to train them with very broad data sets. And I first talked about how we might be able to collect broad and diverse experiences. We saw that a small amount of guidance can really go a long way towards guiding that data collection process. And also we can already collect pretty decent interactions across different labs and environments with even just kind of random scripted data collection. And then lastly, I talked about how algorithms can learn from very broad robot data and broad human data. And we saw that broader data leads to broader generalization, perhaps unsurprisingly, but the important bit is that we can start to get robots to generalize much further by building algorithms that can learn from this broad data set. And also videos of humans seem to be a pretty promising data source for robots. And all of this is really steps towards robots that can not just perform well in one training environment, but that can generalize to new objects, to new environments, to new camera viewpoints, and so on and so forth. A couple open questions that I'll bring up. I think in robot learning, I think we really only started to scratch the surface of these really broad, scalable data sources. And I think we should think about accumulating broader, more useful robot data. I think that things like Robonet are a step towards that, but we need to collect, we probably need to further scale up data collection and also collect more useful data at this sort of level of scale. And I also showed about how we can use videos of humans for learning reward functions, but what about using them for control and for learning policies? We have some initial works in this direction that were published last year, but there's still a lot of work to be done in this direction, especially using it for generalizable control. And then the last thing that I think is worth thinking about is not just scaling up the data and generalizing well because you have a broad data set, but also trying to go beyond the data distribution. And we have some ideas towards doing this, including trying to get robustness to domain shift by adapting to distribution shift, and also kind of trying to get robustness to changing environments by also kind of fine-tuning on those environments. But I think that this is really still an important open question that we need to be thinking about. And with that, I'd also like to thank my students and collaborators, especially the students who were kind of leading a lot of the work that I presented today.
Cool, awesome, thanks a lot. This is really a lot of work, actually. Really awesome progress in this area. So we have time for a few questions. I might start with the obvious question, I think, to me is like, you mentioned a little bit at the end, is the solution to scale up more data and have bigger models? How far do you think we can get with that, right? Like, what you mentioned is, well, of course, the distributions need to be reflected, but at the same time, you also mentioned that, like even big models might still suffer from underfitting if you did have that kind of data. So is it just, oh, we wait for 3 or 4 more GPU generations and it's just gonna solve a lot of these problems? Or do we need to do something different there? What's your take on this?
Yeah, lots of thoughts on this. I think that one thought is, well, I think that like there are still open questions on the data collection front. I think that we've kind of made progress on that front, but even just like getting really high quality, very broad robot data is pretty difficult. On the modeling front, I think that there's 2 things that we need. I think that we need to scale things up further. I think that the model, like we could certainly train larger models. I also think that ideally we would figure out methods that are a little bit less prone to underfitting. And I think that video prediction models, the architectures that we're using, it's possible that those architectures are more prone to underfitting than others. And also, I think that there are some approaches that might be less prone to underfitting because they don't try to model everything about the world. I alluded to this a little bit in terms of like learning representations that are particularly like useful for control, for example. But there are also model-free approaches, sort of like goal-conditioned reinforcement learning, for example, where instead of learning to predict the future, you try to learn kind of, given the future, what actions should I take? And it seems possible that those might be less prone to underfitting because you don't have to generate everything about the future. You just you have more of a discriminative model. So those are some of my thoughts. I also think that compared to the rest of machine learning, in many ways, I think we haven't really actually started to get towards the scale. I think like some of the work that I presented have moved towards the scale of the rest of machine learning, but I think that we really haven't done it justice in comparison to the amount of work in machine learning that has used large data sets and so forth. And machine learning has seen so much success with that recipe. And so I think that we should at least try to replicate some of that success in robotics.
I'm like coming from a slightly different area like graphics and so on. Like, I know there's a lot of work on synthetic environments and simulation right now. How far do you think you could get with that, in a sense that, I don't know, I could imagine you using even active learning, you're just generating data on demand when you need it and, train your policies that way. Is that something you're currently looking at, or?
Yeah, so it's like basically training and simulation and trying to transfer things to the real world is certainly a pretty popular approach. And it's something that we're looking into a little bit. There are a couple downsides to it. The first downside to me is that there is less of a very clear success story of that sort of approach compared to the success stories that we've seen in machine learning. And then the second is that one of the challenges with doing that is to really get it to transfer effectively. It often requires a lot of engineering on to create an environment that looks like the real world. And you kind of domain randomization, the idea behind that is to really broaden your simulation environments with lots of backgrounds and so forth, but broadening in a way, it's easy to broaden in some dimensions like backgrounds, colors, that sort of stuff, but broadening towards lots of different objects and lots of different object arrangements and so forth, I think that that often requires a lot of engineering. And in contrast, if you just put a robot like in your bedroom or in the real world, you get all of that diversity for free almost.
I see. So you're saying it's even harder with synthetic environments. Interesting. I mean, obviously, like, again, like the one problem that we experience a lot in synthetic environments, the diversity is even lower because you don't have the right 3D assets. Like what you're kind of saying, right? Like this diversity of the real world. So sure, you can render different viewpoints, you can maybe relight it, but the textures, materials, and whatever rendering from the 3D models is just not quite there. So maybe that's an interesting thing, right? I don't know. I was always dreaming of this thing. Oh, you can kind of have a closed loop. So you learn how to model even in order to get then better transfer, but not just in robotics, even in like standard computer vision tasks, there's not, as you say, there's not that many success stories, which is, it's a bit sad. I thought this was super cool and it was super nice, right? We could kind of work on it. And also in the graphics community, not a lot of people have looked into it, right? Like what rendering do you have to do and stuff like that. It's not that explored, it's surprising. So either it's just fundamentally difficult or we just haven't figured out the right way yet. Anyway, kind of cool. Anyway, any other questions? Anybody on Zoom has some questions? We have a lot of questions on YouTube already, but I wanted to ask people here if somebody had a question.
Hi, yes, I have a question. So thank you for this amazing talk on robotic meta learning. It's very interesting, especially this idea of basically showing videos of human performing tasks and then like letting the robot trying to infer what it has to do itself. I guess there's a lot of potential there. And what I wondered there is, like, since this kind of like imitation learning, what it basically is, I guess it's quite hard because the robot is seeing humans and it is a robot itself. So what it will observe later is quite different from that. And I wondered if people are looking into how to kind of gap the difference in the domain there and do things like, I don't know, predict the skeleton from the human videos and predict a skeleton from the robotic videos and try to kind of like match that, because it's, I guess the similarity between a human and a robot is just the skeleton. Are people looking into that? Is this helpful?
Yeah, I guess first, I think that would be pretty helpful. And if people could look into that, that would be awesome. As someone who's a little bit less of a computer vision person, it's not something that we are in particular looking into, but I think that that's like kind of one direction that I think could be quite helpful. And one of the reasons why it could be quite helpful is with these videos of humans, we don't have like the actions that the human took. And if you had that actions, it'd be much easier to plug this into reinforcement learning algorithms and to the algorithms that we use for control. And even just with the skeleton, you can kind of back out the actions because you can back out the difference in skeleton. I'm not 100% sure if the problem would be like, if we'd be able to fully solve it if we had that component, because there are other challenges like difference in morphology. The robot does the task in probably a different way than the robot does because of that difference in morphology, and so forth. But I do think that bridging the domain gap between robots and humans could be really, really helpful for making progress on this problem.
I see, thank you.
Any other questions?
Hi, I can ask a question. Thanks for the talk. So I think you kind of alluded to this in terms of learning representations, but can you give some intuition as to why you want to predict videos in sort of this pixel-wise generation when the robot itself will be making movements in a very different domain than the image video domain?
So the main reason why we want it, for like learning these models, the main reason why we want to predict video is that it's really easy to get a lot of data of videos of robots doing things and actions, and getting other supervision is much more difficult and costly. And it's also not really clear to me what that supervision should even be, especially if we move towards things like deformable objects, where there isn't really a clear representation of what the object should be. Does that answer your question?
So like if you have this object segmentation or something like this, and you operated more on the some kind of higher level primitive than a pixel by pixel basis, then you might be able to get more information about the actual robot object interactions.
Yeah, I guess in terms of segmentations, I mean, if someone wanted to label the data set with like segmentations, that would be great. From what I understand, like getting segmentation labels is pretty expensive and costly. And so we haven't pursued that too much. And in some ways, it's kind of similar to the kind of failure case that I talked about earlier, where we tried to run basically things like mask-RCNN, for example, off the shelf on like these sorts of images, for example, and it really didn't work very well at all. And the same is true for basically a lot of the other images that I've shown. And so the kind of the main reasons why we think we haven't really pursued that, and we've pursued more self-supervised approaches, is because the annotations are expensive, and oftentimes I think that the annotations wouldn't just be a one-time thing. Whenever you want the robot to like interact with a new object or a new environment or something, you might need like additional annotation for each new environment.
Yeah, definitely the annotation problem is complicated. I was just wondering, because the robot arm views seem to be more segmentable in the sense that when the robot moves something around, whatever is changing is probably the object segmentation in this case, right?
Yeah, certainly. And I think that there could be self-supervised approaches to try to get that sort of segmentation to get across, to try to sidestep the annotation issue. And I actually think that there are some papers that do that. The other thing is that even if we did have the segmentations, it's not like 100% clear that that's enough information to solve the task. And so, I think it's, in some cases, in some tasks, it certainly would be, I think, like if you just want to, for example, like move the apple onto the plate, which is one of the tasks that I had here. For that, like I think you only need segmentation. But for some of these other, some other tasks, I think that you might need more information than that.
Yeah, thanks.
How much do you try on like, I don't know, generic self-supervision things? I don't know. The one thing I would do is I would probably put like 5 RGB cameras from different angles on it, put a bunch of depth cameras on it, just record all the data, and then, like have like contrastive losses between different viewpoints, and just learn a better feature representation for free, right? That gives you some kind of spatial understanding. And by the test time, you would still test with a single RGB stream, right? So I don't know. I mean, we've done this now a little bit so I don't know. We have one paper in submission right now where we're basically learning multi-view constraints for pre-training, and that actually outperforms ImageNet features because you're kind of learning like 3D structures for free. And I feel here this must help a lot because you get all these correspondences in the spatial layout for free.
Yeah, I think that could potentially help a lot. We haven't explored it too much, although there is a paper called Time Contrastive Networks by Pierre Sermonet that did something like this a few years ago, and they had actually had pretty good results there. I should also mention, actually, these videos in particular were all with 2 camera viewpoints, because you do actually need to resolve some depth ambiguity. If, for example, like you tell it to like move the apple to a certain place in the image, there's depth ambiguity there. And so we actually use 2 camera viewpoints both during training and during testing. And in the Robonet data set, that does actually have a lot of different viewpoints in it, including, I think, information on the synchronization. And so trying things on that could be pretty interesting and cool.
I mean, I can see
we don't have depth data.
If you have multiple viewpoints, you can just run a stereo match also, right? It's perfect, but at least you get a bunch of constraints, even if it's just a bunch of sparse constraints, right? So I don't know, you run a SIF matcher, you get a bunch of key points, you're gonna estimate a few depth points. Even these proxy losses, I mean, I can see why like using a pre-trained mask RCNN is not gonna help you too much. It's just, you know, I don't know, like I think you have to train it jointly in a multitask fashion. Otherwise, it's probably not gonna give you much better features than what you're getting already. But I feel, I don't know, like, I mean, I really like this idea what you're doing there with these hierarchical autoencoders, right? This kind of, like, you're trying to make sure you're not running into these local minimas in order to kind of collapse. And I feel like these multitask learnings could really help there. Like, you know, this, because you're just giving it more constraints. But what's kind of interesting, like, that you're saying like, oh, segmentation is expensive because you need labels, so you rather just record more data and it works better this way. This is kind of an interesting mindset from the vision people. They would say no, do it the other way around. But so I don't know. I find this very fascinating, like how you approach the problem actually. Very, very interesting. I don't know. Do we have any other questions? I guess maybe one last question or so. Because we're only a little out of time. We have a couple of questions on YouTube. The other segmentation we have, synthetics we have. No, I think we covered all of them. So I think, yeah, I mean, thanks a lot for the really cool work. I mean, I think this is really impressive because I think people often underappreciate like how difficult these tasks actually are to do and make the robot do actually anything. So that's why I think it's really remarkable progress that you and your team have been making in the last I don't know 3-4 years. So that's really cool. So thanks a lot again for the fantastic talk. And
yeah, thank you for having me. And I think it is indeed very easy to underestimate how challenging this is, given how intuitive and basic it is to do all these things as humans. Actually, one other quick thing I was going to mention actually is one comment that I made before is like you can get all this diversity in like if you just like stick a robot into the real world and or like into your home and so forth. And actually, because of COVID, these particular experiments were actually done in a home and not in a lab, for example, and so forth. And we like shipped this robot to Colorado, which is where the student was. So I think that like doing some of this stuff at home actually, and even, yeah, it's not that hard. And these robots actually aren't that expensive. So if people want to actually get into some of this stuff, I think that it's, I'd love to see more vision people working with real robots.
Cool, thanks a lot. I'm gonna quickly end the YouTube stream. Okay, I don't know, do you still have time or do you have to run or?
I still have time.